Entonces, ¿está grabando? Sí. Bueno, buenas tardes a todos y todas, a los seminarios del Departamento de Física de la Universidad de Chile. Hoy día tenemos al profesor StephenW de la Universidad de Concepción, que nos viene a hablar de información cuántica. El profesor Warburn me estaba contando, hizo su pregrado en Estados Unidos, pero después migró a Brasil, donde hizo su magíster y doctorado en Minas Gerais, en la Universidad Federal de Minas Gerais. Luego trabajó en Río de Janeiro y durante bastantes años como profesor allá, y de hace poquito llegó hace un año a la Universidad de Concepción a integrarse también al grupo de óptica y cuántica que hay en la Universidad de Concepción, donde, bueno, participa en un proyecto conjunto también con donde estaba Marcel y Rodrigo Vicencio, Marcel Clerc y Rodrigo Vicencio, ¿no? Eh, entonces, sin más que agregar, quería dar la palabra no, un par de detalles. Eh, esta vez vamos a ver qué tal funciona, si tienen preguntas entre medio del seminario que crean que es necesario responder ahí bien, alguna duda importante. Les pido que levanten la mano con Zoom y les doy la palabra, ¿ya? Y si no, de todas maneras, al final vamos a tener sesión de preguntas como siempre, ¿ya?
Yeah.
Eso, entonces te doy la palabra, Steven.
Ok, voy a compartir aquí. ¿Se ve la pantalla?
Sí, sí, muy bien.
Yeah, okay. Okay, okay, I'm going to speak in English. I think this is probably, it's definitely better for me and most likely better for you as well. So, well, thank you first, Rodrigo, for the invitation to give this presentation to all of you this afternoon. Good afternoon. So I'm going to give an overview of quantum information. I'm going to highlight some of the things that I think are important, the basic things along the development of the theory of quantum information, and talk about some more recent exciting things that have happened in, say, the past decade or so. And in the end, I'll talk a little bit more about the state of the art of quantum information and tell you about how it's a particularly exciting time for quantum information. Let's see. Okay. So I'm assuming you can see the cursor.
Yes.
Yeah, okay. So as we know, nowadays we have the development of information technology, which we have is extremely rapid, and is thanks mostly to the development of two physical theories that appeared last century. So namely quantum physics, which is responsible for a lot of the hardware components of our current processors, transistors, and so on. And the other major theory, which is extremely important, it was the development of information theory, which of course provides the basis for software and different coding techniques and other things. To cite an example, a very important example is data compression, which of course allows us to send images and videos and so on all over the internet. So even though we're here, we're already talking about quantum physics and information theory in terms of the information technology we have nowadays. The way we process this information, the way we encode it, and the way we handle it is all based on classical notions, classical physics. We encode the information in classical bits and so on. So let's see. Okay.
Steven,
so
before you continue, there seems to be some problem with your sound. That is sounds something quite metallic. I don't know if it's your microphone or.
No, yeah. How about now? Is it still the same?
It's about the same, yes.
Yeah. Yeah, I just have the microphone on my computer.
Okay, that's okay. I think.
Yeah. Okay, I'm sorry.
That's okay.
Yeah. Can I ask you, okay, so yeah, so the idea so as I was saying, the information technology which we use in our laptops and cell phones is based on quantum physics and information theory, but we process the information classically. So the idea of this new theory called quantum information is to unite, say, the elements of information theory, such as different ideas in communication, cryptography, and computing, and so on, to unite this with quantum physics, and in particular, the kind of strange aspects of quantum physics, or the aspects that were considered strange at the beginning of the theory. And here I'm talking about quantum uncertainty, quantum entanglement, wave-particle duality, and so on. And so the kind of, the idea is to see how these kind of new things that appear in quantum theory and which don't typically appear typically in classical physics, at least when we're talking about bits, to see how these are going to influence information processing. So the motivation to do this is, there's several motivations. One of them sort of stems, or two of them stem from this phrase, which is attributed to Rolf Landauer in a paper that he wrote in Physics Today in 1991, and that is information is physical. So there's, in many ways you can understand this short statement, but I sort of understand it in two different ways. The first is that anytime we encode information or we process information, we use a physical system to do that. So necessarily the laws of physics are going to determine how we can process and encode and transmit information. The other way to understand this is sort of the reverse direction. That is, perhaps we can learn things about physics by applying notions from information theory to physics and talking about information in physics and physical laws. And this is certainly something that is proven fruitful to do in terms of quantum physics. So as I'll show you in the next slide, there's a few practical concerns just from, say, an engineering standpoint to worry about quantum physics and information in terms of the development of computers and information technology in general. And of course, the final reason or motivation to worry about quantum physics and information technology in the same sentence is what I call the quantum dream. It's that maybe by including or considering the quantum process of information, we can do something that is not possible to do in classical systems. So from the practical point of view, typically an example to show practical concerns for quantum physics information, we can resort to Moore's law. And so Moore's law, this is Gordon Moore. He was a CEO at Intel. And he noticed, in this sort of empirical observation, or made an empirical observation, that the number of transistors per chips was doubling about every 2 years. So this plot shows from about 1970 to about 2018, the increase in the number of transistors per chip. And so we know that the size of the chips is not increasing, rather it's getting smaller. And so this means that the size of the transistors is getting smaller. And currently the transistors are on the size of a few nanometers. And as we get smaller and smaller, if we sort of extrapolate this behavior into the next decade or so, we will get to transistor sizes that are certainly within the realm of quantum physics. And so the kind of practical question is, will this different way that these different laws of quantum mechanics compared to, say, classical mechanics, will they get in the way of just usual classical information processing? And will we be able to build computers with chips that are so small that they would have to be described or at least considered to be quantum mechanical? So that's one of the practical reasons to worry about this. And people have been worrying about this since, say, the 1980s. The second motivation, or the last motivation I mentioned, which I called the quantum dream, is this idea that maybe we can do something beyond what is possible classically. And so that's what I'm going to talk about for the bulk of this talk, the rest. So let's just talk about quantum information. I want to kind of define what it is and describe some of the differences between classical information and quantum information. And these are the things that are going to be relevant when we talk about information processing and communication and so on. So in classical information theory, we encode information in bits. The bit is the smallest unit of information possible. So it's a two-level system. You can, of course, imagine this as being some sort of switch that has two states, on and off, or perhaps two different amplitude levels of, say, an optical pulse or something. And you can encode information in the state of the switch or in the different amplitudes of the pulse. In quantum information, on the other hand, we encode information in quantum bits or qubits. And so any two-level quantum system could be used to represent a qubit in principle. And an easy way to visualize a qubit is using the Bloch sphere. So this is a unit sphere where all the possible pure quantum states, or all the possible states of the qubit are all the different points on the surface of the sphere. And we can define two states, say 0 and 1, as something we typically call, say, the computational basis. And these we associate with the eigenstates of, say, the Pauli sigma z operator. So in general, an arbitrary qubit psi can be written as a superposition of the state 0 and 1, where the amplitudes are given by the cosine and sine of, or given in general by these angles in the sphere. So, wait, I forgot. So something I should mention is that because the qubit corresponds, or all these different points on the surface of the sphere are possible states of a qubit, in principle, the qubit can assume, say, an infinite number of possible states, as in contrast to a classical bit. However, when we go to measure this qubit, we do a classical measurement. At most, we can generate, say, one classical bit of information through this measurement. So, for example, if I do a projective measurement along some, with respect to some basis, I'm going to project either onto state 1 or state 2, some arbitrary states in the Bloch sphere with some probabilities. And since there's two possible probabilities, the largest amount of information I can generate like this is 1 bit. So although, say, you could encode, in principle, as much information as you want in a qubit, the most information you can recover from it via a measurement is 1 bit. So another aspect of quantum measurements, which is different from, say, classical physics, is that you can do measurements here that are truly unpredictable, in the sense that if I, say, prepare an eigenstate of the sigma x operator, which would be this, say, a state along this orange arrow here along the x direction, and I do a measurement in the, say, sigma z basis, I project onto the basis defined by 0 and 1. Well, quantum mechanics predicts that the output probabilities are going to be each equal to 50%. And so, this is, I mean, predicted by the theory, completely random. And so this is a kind of, say, quantum coin toss, in which you can have heads or tails with 50%. The difference between, say, this quantum coin and a classical coin is that it doesn't matter how much information I have about the system, or how powerful of a computer, or how good I am at doing calculations, I still cannot improve that 50% prediction probability. Essentially, I'm completely ignorant of the result. It's completely random. And so, I mean, as I say, so in this sense, it's truly random, as opposed to, say, a classical coin, where if I knew exactly how I was flipping it, and, you know, the wind resistance of the coin, and so on, and I was really good at doing calculations, I could predict how the coin was going to land, head or tails. And so it's not a question of it being just a complex problem, it's truly unpredictable. And so, of course, this idea of this quantum coin toss is the basis for quantum random number generators, which has been a kind of a commercial technology for about 20 years or so. So another aspect of quantum information, which is different from classical, is that it cannot be copied. So this is embodying what's known as the no cloning theorem. And so the no cloning theorem is really quite beautiful, because you can prove it in 1 or 2 lines of a very simple calculation. And the general idea is that if you suppose you have some arbitrary quantum state psi, and you want to make a copy of it. So you're going to have the state psi, you're going to have some quantum state that's, say, the blank paper you're going to copy it onto, and then a blank physical system, say, and you have some transformation that's going to realize this copy operation. Well, you can show that necessarily this transformation would have to be non-unitary and non-linear. And we know that quantum mechanics is both unitary and linear. So this sort of operation, or I guess I should say, this perfect copying operation is prohibited by quantum mechanics. I should say, so emphasize again, you can copy with where you pay the price of a loss in, say, the fidelity of the copies which you produce. And of course, you can copy if instead of arbitrary states, you have a set of states which are all orthogonal among themselves. So this means that you can copy classical information. So of course, we know we can go to the Xerox machine or we can copy files on the computer. That's not, of course, prohibited by quantum mechanics. So with this sort of ingredients, now I want to talk about some of the applications in quantum information, and I want to start with quantum computation. So the first question is, so what is a quantum computer? So a kind of real general image of a quantum computer is just a unitary transformation U, which is going to take some initial state of these quantum bits, which we initialize and say this is some arbitrary state like 0. And this unitary transformation is going to transform them into some output state. And then in the output state, I can imagine a couple possible things. I could maybe measure some of these and have classical bits as output to my quantum computation, or I could also have the quantum state or parts of it and so on as output of the computation. So it's a real simple idea, an input state, a unitary transformation, and then some sort of classical and or quantum output. So a really important result that important for several reasons, which I'll briefly discuss, is that it's possible to define universal sets of quantum gates. And so basically what this means is that you can decompose this unitary operator, which acts on n qubits. So this is 2n by 2n matrix, right? You can decompose this into unitary operations that act on single qubits or pairs of qubits. And so there's a number, an infinite number of possible ways you can do this. But typically a universal gate set has a handful of gates and that allow you to reconstruct this unitary to within a given precision, right? And so with this sort of basic set of gates, this is of course important because it tells you, okay, if you're going to build some sort of hardware device that's going to do quantum computation, it doesn't have to perform any, gigantic unitary possible. It has to be able to perform a handful of gates, and then you can construct them in a certain way to do whatever computation you want to in principle. This is, of course, is important from this hardware point of view, and also from, if you want the point of view of, say, computational complexity, if you want to figure out how many operations are necessary, it's a lot easier to count these sort of standard gate sets than to consider these large, most general unitary operations. So with this sort of this idea of these quantum gates, you can then design quantum circuits. And so basically the quantum circuit is composed of these horizontal wires, which basically just represent the evolution of the qubit through your circuit as you apply these different gates in a sequential order from left to right. And then at the end, you have measurements and outputs and so on. So this is what's known as the standard circuit model of quantum computation. And as I mentioned, this is, say, a universal model for quantum computation in the sense that you can implement any unitary to within some arbitrary degree of precision. So what can you do, or how does quantum mechanics help you in computation? Well, that's say a difficult question even to handle in 50 minutes, but I just want to give an idea, a taste of how this works. So imagine you have some unitary operator UF, and so this is going to allow you to sort of imprint the function f onto the output of these quantum bits. So if you start with the first quantum bit in a superposition between 0 and 1, and the second quantum bit in 0, you can construct this unitary operation such that the output is something like this. So this function f is a function of a single bit. So it takes a single bit input to a single bit output. And so here I have a superposition state, right, between the function f evaluated with argument 0 and then with input 0, and then the function f evaluated with input 1. So this is a superposition of the two possible function evaluations I have for this simple function. So there's this sort of quantum parallelism in the sense that with one application of the unitary U, I have these two evaluations of the function f. But of course, the difficult thing is how do you harness this superposition? Of course, if I were to measure the first qubit in either the 0 state or in, say, the computational basis, the 0, 1 state, I'm going to have the state f of 0 or f of 1 with 50% probability, which would just be the same as randomly evaluating f of 0, f of 1. So there's really no advantage to doing that. The name of the game here is to design clever algorithms that allow you to discover information about the function f, but they don't really allow you to discover the function f itself. So for example, if you simply change the input to the second qubit, and I'm not going to go through this, but if you change the algorithm slightly, you can have it such that, and you can perform a measurement, say, on the first qubit in such a way that you can discover whether the function f is constant or not. I mean, f is a function taking a single bit to a single bit, so it's either what's called constant or balanced. And so you can discover this information about the function f without actually discovering what f is. And so, and you can do this in a single evaluation of the unitary u. So as opposed to classically, you would have to discover if f is constant or not, you would have to evaluate f of 0 and f of 1 and so on. So this is a very simple example. It seems, of course, completely trivial, but you can extend this idea to larger and more complex problems. So there's a few examples of quantum algorithms, and by far the most famous and most exciting is perhaps Shor's factoring algorithm. So this is an algorithm to find the prime factors of composite numbers. It gives you an exponential increase or exponential decrease in computation time in terms of the size of the problem. Another kind of famous quantum algorithm is Grover's search algorithm, and which allows you to find information in an unstructured database, and it gives you a polynomial gain over the classical algorithms. And there's also some algorithms based on the quantum version of random walks. Also optimization using a type of computation called quantum annealing, which I'll describe briefly in a few slides. And there's also the idea of quantum simulation. And so back in 1984 and 85, it was Richard Feynman who pointed out the fact that it takes a very large classical computer to simulate even a small quantum system. So the idea being that if you have, say, n spin 1/2 particles to describe the general spin state, you need on the order of 2 to the n complex numbers to describe the amplitudes. And so the idea is that to efficiently simulate a quantum system, you have to use a quantum system, which would be the quantum computer or quantum emulator. So in terms of Shor's algorithm, so just to show you what this exponential gain means, say, in terms of factoring. So I should mention that factoring and other problems related to Shor's algorithm are extremely relevant in, say, cryptography. So for example, RSA encryption is based on factoring. And so there's this big push there's a lot of interest in finding faster algorithms for factoring. And of course, the quantum computer would be a threat to crypto systems based on factoring and other problems similar. So this is just to show you in terms of what sort of time we're talking about. So for example, the yellow curve is I plotted the complexity in terms of operation time using the best classical algorithm at a classical computer operating about 10 gigahertz clock rate. So you can see that to factor a number of about 1,000 bits in size, you're talking on the order of, say, 1,000 years. Whereas a quantum computer, if you could have a quantum computer that would be large enough to factor a number of that size, 1,000 bits. So this is, of course, not considering any sort of noise in the quantum computer. You could do this in, say, a fraction of an hour. Here's the star here is, I found this recently, this was interesting. So someone reported, factored a 768-bit number using a few hundreds of computers acting in parallel and some clever division of the problem. And it took them about 2 years to factor this 768-bit number. Also, this circle here is a more recent estimate or say a reasonable estimate of, say, a quantum computer with about 1,000 accessible qubits operating about 10 megahertz clock rate, including, say, a reasonable estimate of the errors of these quantum gates, and they estimate that it would take about a day to factor a 2,000-bit number. So, I mean, so these sort of curves here, of course, are some sort of ideas of bounds or and whatnot, but you can see that the estimates are still not very far from what's expected from the complexity analysis. So I mean, this is, of course, I would say the main motivation for building a quantum computer would be this exponential increase in efficiency in factoring. So I also mentioned adiabatic quantum computing, in particular this idea of adiabatic optimization. And so I'm going to mention this here for two reasons. One is that it's just kind of physically a beautiful idea. And the second reason is that this is the basis for the Google quantum computers, the D-Wave computer, which is, they report having a few hundred or even 1,000 quantum bits. It's not actually a universal quantum computer. It's what's called a quantum annealing device. So the idea here is that if you have some problem, so like an optimization problem, so you have some set of constraints, and you want to find a solution that optimizes, say, the largest number of constraints. And so the idea is that if you can encode this problem into a certain Hamiltonian of the system, such that the optimal solution which you're looking for would be the ground state of the Hamiltonian, since it minimizes the energy. And so the idea is that you can start your system in some known ground state of, say, a simpler Hamiltonian, and then you can change parameters of the Hamiltonian h of 0 and take it into Hamiltonian h of 1. And if you do this adiabatically, meaning you do it slow enough so that your system never leaves the ground state, essentially you evolve the ground state of the known Hamiltonian into the ground state of the more difficult one. And as you can discover the ground state, you discover the optimal solution. So this is kind of an interesting idea. And of course, how efficient this is and so on depends on how fast you can change the parameters. And there's lots of physical analysis that you can do to talk about how long it takes and so on. And so as I mentioned, this is not a universal model, but it's relevant in particular, given what we hear in the news about quantum computation nowadays. So yeah, so this idea, so the idea of quantum computation is in my opinion, a beautiful idea. There's some interesting applications. And of course, I mean, the reason this is a very tough technical challenge. And of course, the reason is because quantum information is fragile. I mean, we don't see quantum phenomena every day. Typically, you have to spend a lot of money to observe in the laboratory. So this noise in terms of quantum systems is usually called decoherence. Another type of noise you can consider is losses, which I'll kind of talk about these separately and at two different times in the talk. And of course, this decoherence, this noise is the largest obstacle to this quantum technology. So the main idea behind decoherence and why it's such a problem is that, well, or why quantum systems are fragile is that if you imagine, I mean, we have this block sphere of all these possible states. So of course, we have this essentially an infinite amount of possible things that can go wrong if you think about it. So, I mean, a classical bit, a 0 can flip into a 1 or a 1 can flip into a 0. That's about all that can happen. Here, if you prepare a state 0, it can rotate in any direction and end up in any other state in the block sphere. And typically this happens sort of probabilistically, depending on what the environmental conditions around this quantum bit are. And so because this is probabilistic and you don't know you don't know what's going on, your pure state psi gets transformed into a mixed state rho. And there's a kind of really interesting way you can visualize this in a general way is if you imagine, say, the block sphere of possible states here on the left. When you have a decoherence process, it deforms the block sphere of possible states. So in this particular example, the block sphere is getting transformed into this sort of ellipsoid, this egg-looking object. And so this is, if this process were to continue on and on, sort of to the limit in which this egg turns into, say, a straight vertical line, we would be reduced to, say, a classical system. So we would destroy all the coherence in the system, and we would just have a vertical line of states that would be statistical mixtures of the 0 and 1 state. So this is essentially the transformation of a qubit into a classical bit. And so this is you say that, you know, how you can visualize, say, the quantum to classical transition of a qubit. So given that decoherence and noise given that quantum systems are so fragile, an early question in say the 1990s or even earlier was how can you correct for errors? Or is it, maybe a better way to state that question is it possible to correct for errors? And there was maybe good reason to be skeptical, because in classical computing, what is used is just redundancy. So you can make copies of classical bits, which is completely allowed. And then if, you know, some of them flip or there's errors in a few of them, as long as the majority are still in the original state, you can kind of just take the majority rule. But as we saw, you can't copy quantum information, you can't copy arbitrary quantum states. But as it turns out, and this was discovered in the 90s, and this is, I mean, extremely important, you can do a quantum error correction using a very similar idea. And so the idea is that, well, just to give an example to show how this is done, if you just imagine simple error, and we'll just consider sort of the classical error of the bit flip, meaning that the 0 flips to 1 and 1 can flip to 0. And imagine this happens with some small probability. Well, you can use this idea of redundancy where you define the 0 and the 1 states as new states, but now they you define sort of what are called logical qubit states, 0L and 1L, and use 3 physical qubits to represent them. So 3 zeros represents a 0 and 3 ones represents a 1. Then when you encode information, for example, you make a superposition state, you make a superposition state of these new logical states. So, so here I have 3 qubits used to represent one, say, logic qubit. And so now in this model we're considering, because the error probability is low, well, there's sort of 4 things that can happen. Either there's no error, or say one of these qubits is going to flip. So, so what's interesting here is that you can do a measurement actually on the system. You can do a measurement that's defined by these 4 projectors, and you can discover what happened. So you can discover there's no error, or if there was error in the first qubit or the second qubit or the third qubit. And the idea is that these projectors project into a subspace, or say an error subspace. So the subspace of 0 errors, or the subspace of error in qubit 1, or qubit 2 and qubit 3. And you can do this in such a way that you never discover information about the quantum state. And what I mean by that is you never discover alpha and beta, and you never collapse the quantum state so that you lose the information about alpha and beta. So if you can discover the error subspace, then you can go and you know exactly where the error is and you can correct it. And so this maybe seems a little trivial because I'm just talking about a single bit flip error. As I mentioned, there's an infinite number of things that can go wrong. Well, as it turns out, you can kind of decompose these general quantum errors into a few combination of a few simple quantum errors. And as it turns out, they end up being flips, but with respect to different eigenstates of the Pauli operators. So you can have a bit flip in the sigma z basis, or a flip in the sigma x basis, or the sigma y basis. And so if you can correct all 3 of those errors, you can correct any error. And so since these bases are all sort of equivalent to each other, by just rotating the sphere around, this general recipe for correcting a sigma z error, also, you can change this a little bit and also correct the others. So with a slightly more complex code, you can correct any error, assuming that the error probability is low. And in fact, well, you can even make it less than this, but with 9 qubits, you can have a protected logical qubit. So there's this overhead of, in the order of about 10, an order of magnitude to do error correction in this simple scenario. So as I said, this is of course very important because it gives you, it basically gives you a proof of that quantum computing could be viable. I mean, there is a way that you can correct errors, and it's not going to be easy, but at least in principle, it can be done. There's no physical barrier to correcting errors in a quantum computer. So now I would like to switch gears a little bit and talk about quantum communication. And so the kind of two main things I want to talk about here, we could talk for a week about quantum communication, but I just want to talk about two main points. And one is how quantum physics allows you to send secret messages in quantum cryptography, and talk about quantum communication for transmitting quantum information. So quantum cryptography actually is what's known as quantum key distribution. And so the idea is that in classical cryptography, there's an encryption protocol, encryption system called the one-time pad, which was introduced in the beginning of the last century. And the idea here is that you can use what's known as a secret key. So this is just a sequence of random bits. And you can add the sequence of random bits to your message, which would be another sequence of message bits. And so you can use this to encode, and then you can use the same sequence of bits to decode the message. So this is a method for sending a message, encoding a message and decoding a message between two parties who want to communicate in a private way. And so around World War II, Claude Shannon showed that this one-time pad is completely secure. I mean, he used information theory at the time to show this is a completely secure protocol, as long as this encryption key is composed of random and private bits, and as long as you use the key only once. So this is kind of this is important. It's a sort of security proof, but it sort of just shifts the responsibility from having the messaging system to sending the secret message. Now you have to figure out how can you share these private keys. So as it turns out, quantum physics provides a kind of really beautiful solution to this problem of how to distribute keys between two users, and that's why quantum cryptography is really about quantum key distribution. So the idea here, again, as I mentioned, is pretty simple. We have, say, party A, who, so what she's going to do is encode 2 bits of classical information into 4 non-orthogonal states of a single qubit. So say she could encode these 2 bits she could prepare a qubit in either one of the sigma z eigenstates or one of the sigma x eigenstates. She's then going to send her qubit to party B, who's going to measure the qubit either in the sigma x or the sigma z basis, say randomly. And so since they're collaborating with each other, after B does the measurement, he can then talk to A and decide whether and determine whether he measured in the same basis that the qubit was prepared in or not. And so they can discard the cases where they prepare and measure in, say, different bases, and they can keep the cases where they prepare and measure in the same basis. And so if they're both working the same basis, then his measurement result should completely correspond to the bit she sent. And so if she chooses these randomly, he then has the same sequence of random bits. So if they do this many times, he would have the same sequence of random bits as she does. So this is a way to distribute the key. However, of course, you want to make sure that this is private. And so the way to do this are through sort of complicated security proofs where you consider an eavesdropper. And the point here is that the eavesdropper has a hard time given the fact that A is encoding 2 classical bits into a single qubit. Because we know that, as we mentioned, the eavesdropper cannot copy the qubit perfectly. If she were to do a straight measurement on it, at most she can obtain 1 bit of information, which is not enough to know which state was encoded. And also anything she does here on this qubit, and if she intercepts it in the transmission line and measures it or does whatever, it's going to end up perturbing the state. So then if she's trying to stay hidden, she's going to have to, say, do a measurement and then replace the qubit. But since she perturbed the state, she doesn't have all the information. She's going to replace it with a qubit that's, say, slightly different. And this is going to cause errors in the key that Bob has, or excuse me, that party B has. So what A and B can do then is compare a certain subset of their key and see if there's errors or not, see how many errors there are, and then they can determine whether there was an eavesdropper or not. And if there's an eavesdropper, they just discard it. I mean, the key is only useful, the key is only important if it's used to encode a message. And so they can discover the security of the key before it's even used to do anything. So, here we have this big motivation. So this is would be, of course, this is all in these security proofs. You use sort of basic principles of quantum mechanics to prove the security. And so this is, of course, this is a provably secure method of cryptography, and it involves sending qubits from one person to another, typically over large distances. And so this is a big motivation for quantum communication, to send qubits around. So, now I want to get to so in terms of quantum communication, the big problem here is, well, of course, noise in the channel, and even more so is the problem is losses. So as we mentioned, quantum information cannot be copied, and so that means that these qubits, these signals of qubits of quantum information can't be amplified, as is done in classical communications. Typically in classical communications, you have some input signal, you send it through, say, a lossy channel, you lose intensity, but then you send this signal into an amplifier and you can amplify the signal and send it on its way. So you can do this every so often and deal with the losses. However, in quantum physics, we don't have that luxury because, well, of course, losses are going to either destroy our state or at the very least perturb it in some way. So we're going to lose information. And if we take our quantum state and try to send it into an amplifier, the best we can do are produce, say, imperfect copies. And so we end up losing the information. So one of the obstacles in early quantum communication was, how can you send quantum states in these lossy communication channels? So the trick here is to use what's known as quantum entanglement. So quantum entanglement is a correlation that can appear in quantum systems. So for example, in our laboratory in Concepcion, we use nonlinear optics. We shine a laser on a set of nonlinear crystals and we produce photons, so a photon pair, which are entangled in their polarization degree of freedom. So here, this quantum state here means that either both photons are produced with horizontal polarization or both photons are produced with vertical polarization. And an interesting thing about entanglement is you can just rewrite this state in a different, say, linear polarization basis. And you would see that it's described as theta plus theta perpendicular, which means that the two photons, doesn't matter which linear polarization basis you analyze the photons in, they're always going to be correlated. And so in this sense, this entanglement, this quantum correlation, that's an entanglement, is stronger than a classical correlation because you can observe this correlation in any basis. And so this quantum entanglement is not particular to photons. I mean, you can create a simple quantum circuit if you want to think about the circuit model, and you can produce entangled qubits in, say, with these states 0 and 1. So this is something that in general, I should mention, also appears in quantum computation. So quantum entanglement is, again, something we could talk about for over an hour just by itself. As I mentioned, it's a quantum correlation. It's non-classical, and you can prove this experimentally doing tests of what are known as Bell inequalities. And Bell inequalities allow you to sort of set a bound for these correlations if they were classical, and so quantum physics violates these bounds. And this has been shown in many experiments. And the kind of really interesting thing here is quantum entanglement is a resource as in quantum computation and communication, in particular in quantum communication. So one thing you can do with entanglement is called quantum teleportation, which is sort of a, let's say, sensationalist name, but it's really a useful thing to do. And so the idea here is that if you have a quantum state phi, and suppose we have two people, say 1 and 2, who have entangled state of qubits, so if one wants to send this qubit in state phi to 2, what they can do is, well, one can perform a joint measurement on their entangled qubit together with the qubit phi that they want, whose state they want to send. They do this joint measurement, they obtain some measurement result, and so they send that measurement result, just the classical information of the result, to the other person, who is then going to apply a rotation on their qubit, and the rotation is going to depend on what the measurement result was. But when they do this, because of the correlations that are the quantum correlations that there are in this quantum state, they can recover the state phi. So So in other words, by using this entangled state together with a few bits of classical information to send the measurement result, you can send a quantum bit from one place to another. And as I mentioned, so this is the idea of, say, a quantum communication channel. It's a way you can send this quantum information without sending the actual qubit itself. Of course, sending this quantum information classically would be impossible because you would have to, say, measure the system and then send the information. When you measure the system, you would destroy it. And even if you did know the state, and if it was some arbitrary state, it might require a very large amount of information to define, the exact point in the block sphere in which you're talking about. So, so this is something that's very useful in terms of quantum communication. And again, this sort of transforms the problem of how to send qubits through a noisy channel, this idea of how can we distribute entanglement through noisy channels. So it doesn't eliminate the problem, but it gives us a road to a solution. And so the idea is that you can do this sequentially in what's known as a quantum repeater. So you can have, say, some entangled states between different, you can have a sequence of entangled states between, say, users who are not very far apart. And when you do a joint measurement on two of these, say, interior qubits, what happens is, and you follow this quantum teleportation protocol, you end up entangling the two exterior qubits. So you have two short quantum channels, and you can entangle them and make one longer quantum channel. And so you can do this sequentially in such a way that you end up with a quantum channel, an entangled pair of qubits between the two ends, and then you could do teleportation. And so this idea is what's known as a quantum repeater, kind of an analogy to the classical repeater in telecommunications. So this is kind of the idea of how to do quantum communication over long distances with losses and so on. Of course, when you do this, it might be that in the end, I mean, these entangled states are fragile, you have noise in the system and so on. It might be that in the end, this entanglement is not very good entanglement, which means that your teleportation is not going to be very good. But there's also a way you can overcome this, and that's using something called entanglement distillation. And so the idea here is that suppose you do this quantum repeater several times and you end up with several pairs of entangled states between the two parties that want to communicate. But suppose that the entanglement is low quality. I mean, there's noise and it's not very good entanglement. What you can do is a joint transformation that's local on this group of quantum bits here on the one side, and this set of quantum bits on the other side. And this joint transformation, it's transformation and measurement. You can create, essentially distill from these three imperfect copies or three low quality copies, you can distill a high quality pair of entangled qubits. And so with this high quality pair, then you can do the teleportation from one place to the other. So this is sort of the roadmap of what we would like to do with quantum communication, say in the long term. And so these sort of tricks, which have these fantastic names like entanglement distillation and teleportation, quantum repeater, are really useful things to build these quantum communication systems. So now I don't know how much time I have left.
Well, that's 5 minutes.
Okay, so let's see. So I want to okay, well, let me see how this goes. So I want to just briefly mention a few real interesting things in quantum information processing that have appeared, say, over the last decade or so. And so the first one of them is called measurement-based quantum computation. And so the idea here is that you can use, so the idea is that this measurement-based quantum computation is an alternative way to do quantum computation that's completely different from what I described before as the standard circuit model. And so the idea here is that you can have this kind of large entangled state of qubits. So, say 8 qubits all entangled in a certain way. And you can make this entanglement initially according to some recipe, and then you can perform sequential measurements on the qubits in such a way that through these measurements, and because of the correlations between the qubits and these measurement results, you can essentially, the qubits at the end of this procedure are going to be equal to the initial state with some unitary operation applied. So through the initial correlations and just measurements, you can implement a unitary operation. And so this is kind of the basic building block. With this, you can imagine large, say networks of or arrays of qubits that are entangled in a certain way, and you can perform these measurements and sort of implement an evolution of these qubits and do a meaningful computation along this cell. And so this is a sort of fantastical idea. I mean, it seems sort of far-fetched. Whether it's actually useful or whether actually this model is implemented or not is will remain to be seen. But an important consequence of this is that it led to something that's known as, very important, that's known as blind quantum computing. And so the idea is that this measurement-based quantum computation is, as I mentioned, is completely analogous to the circuit model. I mean, it's analogous in the sense that it's a universal model. And so this allowed for the development of blind quantum computing. And so the idea here is that you can have some, sort of say a cloud-based computing idea, where you can have a server who has this large entangled state, which is sort of the resource for the quantum computer. Now, the client could be just, you or I, like we perhaps don't have a lot of quantum computing power. We can maybe just prepare individual qubits. And what we can do is we can send these individual qubits to the server, and we can send some, say, instructions in terms of classical instructions, and tell the server what to do. And the server will send us the measurement results. And we can do this in such a way that the server is never discovers what information, what the input data of the calculation is, nor do they discover what program they're doing. So this is a sort of combination of quantum cryptography and quantum computing, in the sense that you can do completely hidden calculations on this computer. And so I mention this because it's something that has developed recently, and is something that's very exciting in terms of quantum computation, and something that quantum, especially as we go into, say, cloud-based computing models, it's something that quantum computation allows you to do, that, or at least to a degree of security that quantum computation does not. And it also highlights the fact that it's, in addition to, say, doing cryptography, it's extremely interesting to be able to send qubits around. So this blind quantum computing is also a motivation for quantum communication. So now I want to just finish up, if I can I go for 5 more minutes? Is that okay? Okay, I just wanted to mention briefly the current state of the art. So in terms of computing and so on, there's several different physical systems which are candidates, say, to build quantum computers. Of course, photons or quantum light is a natural candidate in quantum information because it will be used in quantum communication. It's the most logical way to send qubits around. But then you have these other technologies which are here. And it's kind of a really interesting time now because you have companies, and you've companies with investments of hundreds of millions of dollars to develop quantum computers based on these technologies. So recently, a few years ago, from China reported that they launched this satellite, which inside this satellite is a source of entangled photons, like I described a little bit earlier. And so as this satellite is orbiting the Earth, for about 5 minutes every day, it has a line of sight between these 2 stations in China, which are about over 1,000 kilometers distance from each other. And this satellite can send entangled photon pairs to these 2 stations, and they can do cryptography and other tests of quantum mechanics. So this is, so of course, this is kind of this is the information when they originally reported this, and this is, of course, you can't do that much communication for only 5 minutes a day. But it's very interesting in the sense that you can do all sorts of fundamental tests of quantum physics and test this quantum communication over a distance of, say, 1,000 kilometers. So this idea of the fact that you have these different technologies, and of course, photons are really good for quantum communication, but maybe not the best choice for quantum computation. The kind of idea which is going around now is this idea of quantum networks. So it's the idea that you might have different quantum processors based on all different technologies, and you would send quantum information between them using photons and also classic information. So this of course is really ambitious sort of thing to talk about, but developments are happening really quickly. And I should mention that now you can even access quantum processors online. There's several companies that allow you to run your own calculations or on their small scale quantum computers, which you can access via the internet. So, here, there's I'm not going to talk about this, but there's roughly say 100 different companies invested in this quantum technology nowadays. And here's a kind of graph I made, just kind of showing you what the current state of the art is. So in terms of quantum, so you have small scale quantum devices, which are fairly advanced. The quantum random number generators you can buy, and you can make really high quality ones in the laboratory. There's quantum enhanced sensors, which are some are commercially available, and kind of the most noteworthy comment is that currently in the gravitational wave observatories, they're using squeezed light, which is light which has reduced phase fluctuations to measure gravitational waves. In terms of quantum computing, most of the devices which we hear about in the news are these in this intermediate scale. So we're talking about a few tens of qubits. And the noise involved in the operations is quite high, a few percent. So this means that you're restricted to really small scale computations, and they're kind of right on the boundary of what it could be considered to be the border between doing something that's really beyond the realm of classical computing or not. So there've been some talk in the news about just demonstrating this genuine quantum advantage, what some people call quantum supremacy. There've been maybe one or two experiments, but so right around it at this boundary right now. And of course, the goal is to move all of these applications upward and to the right, so that you can have long distance quantum communication and eventually universal quantum computers, or at least computers that would be able to break encryption factor numbers. So just right before I finish, just to mention, so the main challenges right now are, of course, making better quantum operations, so reducing noise. So this is, using better materials in hardware design, using new theoretical approaches. Of course, you want to, if you can bring the error rates down so that you can have a lot of qubits, you can start to use error correction. In terms of quantum communication, the big challenges would be to build a really useful quantum memory, which is needed to do these linking operations in the quantum repeater. So there's a lot of challenges right now, and as I mentioned, it's a really interesting time. So here I'll just finish with these take-home messages, and that's quantum computing is certainly interesting. There's from just, say a basic science point of view, not to mention the fact that there's these novel quantum algorithms which allow us to do some things faster and better than classical computers. Quantum communication is a way to do secure private communication, and also to send quantum information around for these computing applications. So there's and as I mentioned, it's a really sort of interesting time because of all this commercial investment and so on. Interesting and scary. So that's it. Thank you. Sorry if I went a little bit over time.
Thank you very much. Very interesting. So now we have time for questions, and there's already one from Samir Beleño. You can unmute yourself and ask your question.
Hi, do you hear me?
Yeah.
Yes.
Firstly, thank you for your presentation. It was a good one. And
thank you.
And we know that quantum computers have an advantage over classical computers, as they are based on quantum states which can be 0, 1, or superposition of 0, 1. And on the other hand, we also know that classical computers have 0 or 1 of classical transistors. And my question is, What about if a third state of infinite current is introduced in classical transistor? Will it improve classical computers? So if we keep aside the engineering difficulty to realize it, will it reach a high computational level compared with quantum computers? And just to clarify, I have a good hunch about quantum computing, about quantum computers, but certainly I have some doubts regarding classical ones. I think they can be improved. They can still be improved. So that's the question.
Yeah, I mean, thank you for your question. I think, yeah, so I mean, all of the, I mean, I'm saying this without really knowing this for sure, but I would wager that all of the classical chip companies and so on are still investing a lot more money in, say, improving their classical chips and technology, and I mean, both new ideas and designs, as well as the material science and everything involved in making these chips. So, I mean, this is, if we're talking, say, even the next, say, 40 or 50 years, I mean, the way to do kind of better calculations and faster calculations in general is I would say, it's a better investment to invest in classical computing, because I mean, the classical computers do all sorts of things. Here in quantum computing, we're talking about, you know, a few applications. Nonetheless, I mean, it is interesting enough for some key players. I mean, especially governments, banks, some, you know, tech companies and so on, to invest in this. And so it's how can I say this? I mean, as you know, being an academic researcher, I'm of course interested in this because it's interesting. You know, I mean, it's research. It's something that I find intriguing and so on, and it's something that is fun. You know, in terms of if I, you know, were going to invest money, or if I were worried about this, you know, as a way to invest money and make money, I would bet on you know, say a classical computer. You know, I would invest in a classical computer. So yeah, so I think that, so I mean, if in sort of the short term, is say with the exception of the Shor's factoring algorithm, I would say classical computers are going to be superior to quantum ones for a long time. Even these ideas of this quantum advantage involves these problems which are basically designed just to show the quantum advantage. So the problems which aren't necessarily useful. The real sort of holy grail of quantum computing would be to factor a really large number that you could not factor with classical computers. But there you see that the advantage is huge. I mean, we're talking, you know, hundreds or thousands of years in time. Even if you know, develop really good classical processors and so on, just the exponential advantage of the quantum approach is so large that if you could make, you know, a quantum computer of you know, say, you know, 1 million qubits, you could still do things that would be really difficult to do, even if you had extremely good classical technology.
Thank you.
Yes, I have one question regarding the complexity to keep coherence in the system with the number of qubits. That is, how it increases the complexity to keep the coherence?
That's a great question. So yeah, so typically the decoherence times, you know, I'll just use that general term, decrease with the number of qubits, and in a lot of cases decrease exponentially. So yeah, so it's really hard. So I mean, there's of course the idea of the Schrodinger cat idea, the fact that you have, you know, some large, you know, say macroscopic object, the decoherence time is extremely small. So yeah, it's yeah, so it's so there's a big problem, because as you make these larger and larger, like in a typical quantum computation, you end up entangling a lot of these qubits together, and then the decoherence is a lot faster.
Because you have this plot where you have in the lower x-axis the number of qubits, and the plan is to go to a very large number of qubits. So
yes,
should it be possible, or is just a dream to keep all this system in a quantum state?
I mean, it's a really, so if it's a difficult question, because I think, and it's almost hard to answer that, because I think it's extremely difficult. I don't know, me personally, I don't know how optimistic I am that we'll have like a, say a really good, useful, let's say useful quantum computer of 1,000 qubits, in the next, say, 10 years. That seems really difficult to me. But then I read, in information that some of these quantum computing companies are putting out, and they seem very optimistic. So I'm not sure if that's, something they say because they're looking to get money from investors, or if that's really, they have a plan to do it. And if they have a plan to do it, they're not they're not publishing papers about it. I mean, it's all, top secret at the moment. So I'm skeptical, but I'm also like, keeping my eyes open. I've heard some, bold claims from reputable scientists in the field. And so it seems maybe they know something that I don't.
Okay, thank you.
Yeah.
There's a question from Joaquin Medina? I don't know.
Yes.
Joaquin.
Hi,
Hello.
great presentation. I loved it. My question aims to quantum computation or communication using light. And so the main questions are, what are the limitations for maintaining coherence in the light? Because light is less sensitive to temperature, for example, than superconducting systems, for example. Mm-hmm. And the other question would be, how is quantum information limited by the ability you have to deterministically generate the input status of the system and manipulate them? And according to what type of light you use, like single photons or other states, squeezed light?
Yeah, so that's a great question. So in say quantum computing with light, with photons, or with quantum states of light, so the coherence times are typically long. I mean, you can make these optical circuits on a chip and whatnot, where you can write all these different waveguides and combine them and so on, and make this sort of circuit that would take the role of the quantum circuit. And then the main problem is, as you mentioned, is making different states of light which input into this device. So in order for this device to do something that a classical computer cannot, you have to input, say, quantum states. So as you mentioned, either single photons, which are hard to produce because fairly easily you can make 2 single photons, or maybe even 4, but to make 50 or 100 is quite difficult. So you mentioned squeezing. So the idea is to send quantum states, but squeeze states. So in fact, there have been some papers recently in which they use these sort of large interferometers, send in squeeze states, but then the difference from, say, usual squeezing experiments where you measure, say, quadrators of the field, you measure single photons. So there's this kind of quantum computing model that looks to solve some of the problems, in that you use kind of better sources. So you don't have to rely on probabilistic single photon sources. You can use these deterministic squeezing sources, but then you count single photons, or you count photons at the end. So yeah, so that's something that's an idea that's, again, developed quite rapidly recently. And the optical chip technology is really far advanced already. Like that's something that's been in development for, say, a decade or two. And something else that's happened recently are the detectors. So you need really high quality detectors, really high efficiency detectors. I mean, nearly perfect detectors. And as it is right now, you have, detectors with, say, 90% efficiency. So they're getting there. And that's something that there seem to be people banking on this. This could be a possible implementation of at least, say, medium scale quantum computers with, a few hundreds of qubits, or say, equivalent to, say, a few hundred qubits. But Yeah, so this is certainly a nice model, and it's a contender for, you know, say useful devices in the near future. Yeah.
And regarding the state-of-the-art technology, which way do you obtain better results, like right now or for the next couple of years, like with single photons or with superconducting circuits or squeezed lights, or?
So that's a difficult question. Stuff I've read recently and just, you know, in the news is so it seems like there's big bets being placed, well, on trapped ions. So there's there's a few companies in the world doing trapped ion computers, and there you have extremely high fidelity of the gates. And the problem there is, so extremely high gate fidelity. So when that system sort of comes out, and when, you know, that will be interesting. And the other big claims I've heard are in terms of, again, the photon quantum computing. And so the problem there is that I'm not sure. Well, I mean, there are a few, there have been reported, say, interesting experiments using squeezed light. So, and that's certainly something that's interesting, and kind of the results they reported I thought were surprising. But there's another company that I'm not sure what their model is, but they said they will be able to have photonic quantum computers with millions of qubits. But again, so I don't know if they're using single photons or what. They haven't really revealed this yet, but they've made some really bold claims for, say, the next 2 years. So I'm definitely keeping my eyes open to see what they end up doing. You know, as I mentioned, I mean, I don't really like, you know, keep referring to these companies and so on, because I mean, research is, you know, in these fields has been done, you know, in the research institutions and universities, and now these companies are sort of sweeping in. But the big difference is they just have the investment. I mean, some of these companies have hundreds of millions of dollars, and so you can just really throw money at the problem and hire the best people and so on.
All right. Thank you very much, Stephen.
Okay, thank you. I don't know if there's another further question. Otherwise, I'd like to thank Stephen for this very interesting talk. Well, I really enjoyed it. So I thank you everybody for taking part of this seminar. Thank you, Stephen. And
thank you.
The video is going to be uploaded in the Facebook page of the physics department, and also soon also in the YouTube channel of the physics department. I'm going to send you the link.
Okay, great, thank you.
So thank you very much.
Okay.
I'm going to stop recording.